Howdy, everybody. I just thought I'd share my solution to day 8. I didn't do like a real time, me try and solve the problem video today, but I thought it was an interesting problem. One that again had to do with you, at least part 2 had to do with you really trying to like analyze the data, because I think there is a general solution to it, but it's not clear to me like that you could ever solve it efficiently, at least not that I know of. And so I thought it was a fun problem, and I think so. Let's just kind of get into it. So without getting into too many details, there's actually not much to this one. You're essentially given what you're trying to do is a graph traversal algorithm from point A to point, in this case, ZZ, right? You're trying to get from point AA to ZZ. And the goal is for you to be able to like step through it using these right-left instructions, right? So you start at AA, and the first step you should take is go right, which would be CC, right? So you take the right one, and so now you move to CC, and it says take the left step, and that's ZZ, which happens to be the end. So this one in total took 2 steps. They talk about a somewhat more complex where you have LLR as the instructions you could take. And so you go left, and which takes you to BB. Then you go left again, which takes you to AA. Sorry, you're at AA. You do left, which takes you to BB. You do left again. You do right, which from BB, which takes you to here. And you do that a few times, and eventually it takes you like 6 steps, but eventually you hit right here for ZZ, and it says it takes 6 steps. The point is you continue this like LLRR to in a cycle to step through the thing until you get there. So again, just like really high level, you're doing a graph traversal, but they've given you the instructions on whether or not it's actually a tree traversal of whether or not you're going left or right. No, it is a graph. Sorry. I shouldn't say tree because it is cyclical. But the idea is these are the instructions you take iterating through the things. If you look at the puzzle input, at least for mine, you get a quite big thing, but you get quite a few. I don't remember what there are. There's 100 plus or so of these. So there's quite a few nodes in the graph. However, each of the nodes only have like 2 edges, right? So it felt to me like a really simple way to like solve the problem was just this itself, if you think about it, essentially looks like a hash map, right? It's just a map where you say AA has left and right of BB, 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 whatever. BB 3Bs, right? So my initial implementation, I created an edge structure that had those left and rights. And I thought as opposed to just having actual strings, I would do, I would try and do it in like a more rusty way, so I didn't have to create new strings. So that's where you see these A's are saying the lifetime of these strings have to live long enough, for as the struct itself. If you're not familiar with Rust, this is just a way of the Rust compiler trying to make sure that you aren't using variables that have been freed or variables that are like out of scope, right? In another language like C, it wouldn't be checked at all for you. But in other languages that sometimes that scoping can be done for you. The way that you do it here in Rust is you say this structure and has to have the same lifetime as these 2 values within it, and then whatever's using this structure needs to have that data available to it as long as the structure is there. Okay, and so again, that was a little dive into the Rust lifetimes. Not by any means comprehensive, Probably not even helpful, right? But the idea is I have edges with left and right that represent the left and right edges that you would take based on the directions. And then I decided to do the directions as a enum just to be fun. So you're either going left or right. So how do you create a direction? Well, if it's a left, you just given a character, if it's left, otherwise it's right. We didn't do really any input sanitization. You don't usually do input sanitization for these problems because they assume that it's always going to be good. So this will be the right one. And so then the map is those set of instructions and then a hash map of those edges, right? So I'm literally just taking this and turning it into a structure. I'll have my instructions and I'll have my edges. How does that look when you're parsing it in NOM? Well, the first part of it are the instructions. And so we can say, I want to get as many of either L's or R's as I can from the input. And then I'm going to map over those or iterate over those and turn them into directions. And so that will be my list of instructions. This part here is just to get rid of the new lines, right? So I'll have a new line here and here. I want to get rid of those. And now in my parsing, I'm at like this point right here. And so from there, I can just create a hash map. And I just do a separated list by new line. And then I do a tuple by parsing this right here, right? Like I recognize that the way that it's going to look is you're going to have the key and then this string. Then you're going to have the left node and then this string. And then you're going to have the right node and then you're going to have this string. So that's basically what this saying is. Get an alpha 1, so get all of that. Then look for this tag and another alpha 1, then look for this tag, another alpha 1, and then look for this tag. And that will take you to the end of the line. So if you just do a separated list by new line, that will collect them all for you. And then you can just iterate through them and use a for each to insert them into the list. There might be a way to do this like in a, I don't know, in a more functional style way, but this was simple enough for me. Like what would the functional style, what I mean is you can actually create a hash map from vectors in newer versions of Rust. And so you could potentially like vectorize this or listize it and iterate over it, I guess is what I'm saying, and do a mapping where you create the node and the edges and then collect it into a hash map. Anyway, I won't show you how to do that, but that would be another potential way to do this parsing. I'm curious how you did your parsing. It would be fun to see how you guys may have done it differently. But that gives me my map now, right? So now I have a set of instructions that I can iterate over, and then I have a set of edges that I can traverse through given the instructions that I have. So how does that look like? The function is actually just called findEnd. And this looks a little complex. If you're not familiar with Rust, you can sort of ignore these. What I'm basically just saying is, given my instructions and edges, if you give me a starting point, I'll tell you where it ends based on this end function that you give me. So you tell me how it should end, and I will tell you when I've met that point. So what it looks like for like part 1 right here, you can see I'm reading the input. I'm turning it into my map, and then I'm just calling findEnd where I want to start at AA and go to ZZ. So this is the function I'm passing. I'll say, hey, findEnd function, you'll know you're done when the current position that you're at is equal to ZZZ, all right? So then that's what this function definition is. So how does that actually work? Well, you're just basically for looping through, or I guess like you're going through all of the directions and you're doing them over and over until you get to that point. So you say for dir in self instructions, and you're going to cycle it, right? So if you get to the end, you want to start over back at the beginning. Cycle is a cool function in Rust that allows you to do that. Essentially, once you get to the end of your iterations, it will start back over at the beginning for you. And cycle allows you to do that because you don't know how many times you're going to go through it. So this is just an easy way for you to say, hey, I want to keep doing this. I want to keep iterating over the instructions. So these instructions right here until I get to ZZ. Okay, so then what I do is I just say, hey, get me the edges of my current position. And then I ask myself, what direction should I take in that current position? If it's left, then I should go left. If it's right, then I should go right. And I just keep track of my count, right? And then I test my function. Have I met my end condition? And if I have, I break. If I don't, I just keep looping. And so this will loop a bunch of times. If you run it and look at the solution for let's ignore all this for now. If you look at the solution for part 1, you can see it took 11,309 iterations, right? So it went through this 11,309 times to get to the final solution. Again, part 1 was not very tough. It was literally just a graph traversal problem. So the way to think about it is what it's asking you is, can you turn this data that I'm giving you into a graph? And a map is a great way to do that. You could also it would have been harder to do it this way in Rust, but you could have actually created nodes and created edges to them if you wanted. That's a potential solution. Using a map is usually pretty easy, especially in this case because you're doing lookups. So this felt pretty simple the way to solve it. But if you understand how to create a graph, part 1 wasn't too hard of just looping through it and finding it. So how does it get harder in part 2? Basically, it says, well, you went through the process and it didn't really help you. So you kind of look at the data a little bit more and you realize that actually what you want to do is you want to start at any point that ends in A and follow it until you find a path that ends in Z. So instead of considering the whole string, you're only considering the A's and the Z's at the end, but you want to do it in parallel. So you say, it turns out that I think it turned out that there were 6 of them. Let me run it again and I'll show you. So right here, you can see that there's 3, 4, 5, 6. For my input, there were 6 points that ended in the letter A, and there were 6 points that ended in the letter Z. And the question it was asking you was, how many steps do you have to take such that all of them end at the Z at the same time? So all simultaneously end up at nodes that end with Z. So again, simultaneously start on every node that ends with A. How many steps does it take before you're only on nodes that end with Z, right? So the idea is you now have 6 of them that you're going to iterate over, and you're just going to keep stepping through them one at a time until all of them equal Z. Well, here's my solution. If you step through them manually, it turns out that there's, 100,000 million, billion, 13 quadrillion, 100,000 million, billion, quadrillion, trillion. There's 13 trillion. I skipped a number there, right? There's 13 trillion operations that you have to do to get there, if you do it one at a time. So that's 13 times 6 trillion lookups in your map, which is just unfeasible, right? I can't think of another way to brute force that. So, but the question is, how did I get to this answer, right? Because I didn't know at the time there were 13 trillion. So what I did was I just started looking at the problem, and that's what I want to show you in my code. When I first saw it, I initially did some grepping on it. So you can see I'm like, well, how many end in A, how many end in Z? I had to like count them here because it also found these ones, right? But it was clear that there were 6 and 6. And so then my next thought was, does one always end at another one? Like, is one A always related to another Z? And that was like this part right here, right? So, excuse me. So I'm testing right here. I'm saying, can I call find end on ZZ a bunch of times and always end up back at ZZ? So again, if I run this and show it to you, you can see that AA ends at ZZ, and it turns out that going from ZZ to another ZZ always takes the same amount of steps, and there's not a ZZ in between it. The test that I do is I say, is there any ZZ in between it, right? So, I guess what I should do, it should more be like ends.contains S, like this. And you'll see, so clear. I'm checking. Well, basically what I'm going to do is I'm going to start at ZZ, and I'm going to check all the way through to see what I come upon next. And it turns out, what it turns out is that these steps are cyclical, right? So AA always goes to ZZ, and there's no other thing in between. And it just so happens that that's the case for all of these, right? So I tested it on a couple of them. You can only see me doing it here for the ZZZ. But I did test it on a couple, and it became like clear to my mind that if you are starting at TVA, you'll always end at XKZ, and it will always take you 20,777 steps, right? So how does that help you come to a solution? Well, you now know how many steps each of these ones take, and you know it's cyclical, so they'll only ever land, TVA will only ever land on XKZ after 20,077 steps. So when will they all land on a Z? When will all these A's land on a Z? Only when all of these steps have, like, you double it each time, or you add that many steps each time. Only when, like, they catch up to each other, right? And they end up being equal. They're all equal at the same time. And what is that in math? That is a least common divisor, right? So you probably are most familiar with the greatest common factor. You've heard that, I'm sure, before. Did I say least common divisor? It's least common multiple, right? You've probably heard of like least common divisor as well. It's like the opposite, right? Least common multiple. That's what you're actually searching for, it turns out. You want to know how many times do I have to multiply each of these such that they all come out with the same number, but not only the same number, but the lowest one of those, right? So what's the lowest one? So maybe a way to express it better would be to, like, these are big numbers and they're hard to show, but imagine, maybe I can just show you on a Jamboard. If you already know about least common multiples, this won't make, this will sound a little silly or whatever. You're like, yes, obviously that's the case. But just for example, if I had the numbers 2 and 3, and I want to know when their least common multiples is, you kind of like just keep multiplying them until you get one that's the same, right? So here you eventually land on 6. But this one took 3 steps, right? Or maybe 2. We'd say it took 2 steps. This one only took 1 step, though. And so that's where if you might reason about this and think, oh, I can just keep stepping and try and solve it. And I thought about that at first. I'm like, oh, do I just keep like stepping through these until they're all equal to the same? It still takes a while, right? Because it turns out how many times you have to do it for each one is substantially different, right? This one is 661 million, but this one's a billion, right? So as opposed to doing that, you actually want to do it mathematically, right? And I did not remember how to find the least common multiple, so I actually had to Google it. So I'm going to give credit, though, to the algorithms in Rust. They actually had a least common multiple function, and this is what I used, right? So the least common multiple function is this right here. I won't go into the details of how to do it, but you use this GCD of two numbers to solve it. I think this is the Euclidean way, if I remember right. But the idea is this is an efficient way for you to say, given a set of or a list of numbers, here is the least common multiple among all of them. And so that's all step 2 is I could just say, find the least common multiple of all of my steps. So how does that work? I call find end right here on each of the starts and say, hey, go until I find one of the ends. And once I do find them, I'm going to add the steps to my S, or the number of steps it took that iteration to my steps vector. And now I know that now I have a list of steps, which are these numbers right here, that I can just call least common multiple on, and that will give me the solution. So again, this one was a bit of a trick. There wasn't any time where you just said, oh, I know a graphing algorithm, right? Sometimes the graph algorithms tend to be ones where they're like, oh, I need to do some kind of thing with it, and you end up doing some kind of graph traversal algorithm, or the traveling salesman problem, things like that. This wasn't like that. It was, at least for me, it was a data analysis problem, and so that's something that is okay to think about, or it's okay to do to try and solve the problem. I know I've talked about this a couple times before. You may be trying to solve a problem, and part 1 is super easy. Part 2, you don't know what to do immediately, because you say to yourself, oh, well, I can't just start iterating over these things. And so you just start doing some testing, right? And that's what this code is. I'm going to leave it in here because literally 3/4 of my main function is doing that testing, right? Is where I said, well, how many starts are there? How many ends are there? What are they? And then I started doing some analysis on the starts and ends. How many steps do each of them take? Are all of them unique paths, right? This problem, a more generalized problem of this, you would have had to gone through all the steps. Imagine a case where it cycles between 2 or more of them. That is to say, AAA doesn't always end at ZZZ. So it could be AAA ends at ABZ, and then it ends at ZZZ, and then it ends at ABX, or like CBZ, and then it goes back to ABZ, right? If there's like some weird pattern that would cause it to go that way, because of the instructions you're given, you may struggle to find some efficient solution to do it, and you'd have to do the 12 trillion calculations. So you shouldn't expect to do those 12 trillion calculations, though. Like I've told you before, is like there'll always be some kind of solution to it. And this one happened to be is, hey, if you do enough data analysis, you can discover that the best way to solve this is just through the least common multiple. And like I said, I didn't know offhand how to do the least common multiple. I potentially could have iteratively said, okay, I'm going to go through all these numbers right here and just double it and see if they're all equal, and then I double this one, see if they're all equal. That would have been pretty slow. That's the brute force approach. So instead, I just looked for an algorithm online that solves this. And just like real life, I don't consider that to be like you're cheating. If you don't know the answer to a problem, or you kind of know what you want to do, but you don't know how to efficiently do that, there's nothing wrong with looking that up, right? So that's what I did. I looked up, hey, how do I calculate the least common multiple? And I found these guys that had already do it, these people that had already done it, and that's how I got to my solution. So there you go. That's day 8 in Rust. I thought it was kind of a fun thing to do. I had fun solving it. I actually thought it would be more interesting. I loved the graph parts of my algorithms courses and things like that. So whenever I get like a graph traversal problem, I'm like, ooh, do I get to like try and remember how I did like the traveling salesman or whatever, those type of things. This one turned out not to really be that, right? Because it's really just you're given directions. But it was still fun to do the data analysis. Hopefully you guys had fun too. I'd love to see your inputs, or see how you solved them, I should say. Did you find some other way to do it? Especially if you found a more efficient way than like the 12 trillion calculation step through, or something other than just the least common multiple thing. That would be really interesting to hear from you. Because they usually don't tell you what the intended implementation is, and so it'd just be fun to see some other way of how to do it. So again, love your comments. I love responding to them, and hope you guys have an awesome day and keep enjoying Advent of Code.